start from here. So last time we introduced random variables and we started looking at a few distributions. So we'll pick it up from there and complete a little bit of the overview and then move on. So we did mention the binomial density function. And now one important distribution also is what is called hypergeometric. You'll see why this is called this way. So essentially, this models the situation where we have, say, for example, n of the usual balls in my urn, whatever, and then some of them are white, some of them are black, or anyway, like two different types, right? So suppose that we have m white and then n minus m black balls. Okay, so some parts are white, some parts are black. And now we're extracting some of them without replacement. So if I sample n of them, then I can model a random variable. Arbitrarily, let's say I'm taking m to be the number of white balls, so let's model x to be the random variable that counts the white balls chosen. Okay, and it's clear then that the value of x is for certain event omega less than the minimum between n and m. Okay, so if I have, and if the number I extract is bigger than exactly how many white balls, then at most I can have m of them. Okay, so in the case that I extract like not all the white, or I extract not bigger than, so in the case n less or equal m, then I can model this distribution in this way. Fx of I is equal to, essentially, remember this was the probability that the random variable is actually equal to, and this is equal to m choose I, and then m minus m choose the remaining ones, so n minus I divided by the total. Okay, so it's just binomials, and this is the hypergeometric density function. Remember, up there we did say that the density function is counting the probability of random variable being equal to a fixed value. Right? So for any fixed value, the density function is given by m choose I, and then m minus m choose I minus I. So basically picking how many ways I have to choose I out of the good ones, the white ones, and then the remaining out of the other ones for the total. Okay? And so now, this brings us to one of the most important ones, which was we call the geometric distribution. And this captures the toss of an unfair coin, because so far we always say, like, if the coin is fair, then we have probability 1/2, and blah, 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 right? So now what happens if we have a certain probability p between 0 and 1 of whatever, say heads, okay? And then tails is going to be obviously 1 minus p, okay? Again, if the coin is fair, p is 1/2, everyone is happy, okay, it's the boring one. So let now x be the random variable that counts the say number of tosses for the first head to appear. And in fact, x can take any number of any value, right? It could take even a ridiculously long amount of trials before I get like the one head. So now the density function in this case is calculated in this way. For f(x) of n, this is the probability that x is equal to n, right? So this is counting what's the chance of x being equal to n. So what's the chance of me having to toss n times before I get my first head, right? And this is given by 1 minus p to the n minus 1 times p, of course. Okay? And then therefore a random variable with this density function has a geometric density, and you can see that essentially the sequence of probabilities, if you do this for like fx of 1, fx of 2, etc., they are distributed like a geometric progression that you will remember from like your calculus days, essentially. Okay, so then we will see what the expected value is, and that's kind of like where we're going to go next of this. So now, the first step that we did is move from a single event to like correlated events, and then we're going to have to do the same thing with random variables, right? Because that way we can capture events that depend on each other and random variables that depend on each other, right? So we can define a joint density function right? If we have two random variables like x and y as a function f x y of two variables x and y, right? And this is exactly, as you can expect, the probability that x is equal to x and y is equal to y. Right? That's very nice. Huh? Yeah, so that's the joint density function. And similarly, we can define the conditional density function x given y as of x given y as the probability that x is equal to x given that y is equal to y. Okay, and of course we say that x and y are independent if we have the f of xy is equal to fx of little x times fy little y. Okay? Similar to what we saw for the events. Okay, so we can see one example of this, just to pinpoint what is happening. Suppose that we have an urn, the usual urn, like this, and there are like 4 gold coins and 3 silver coins, right? Coin is drawn at random, examined and returned to the urn, and then we draw another one, okay? So we draw 2 coins, one at a time, with replacement. Okay? Now consider x to be the number of gold coins extracted and y to be the number of silver coins extracted. How do we find the joint density function in this case? We have to calculate what's the probability that x is equal to x and y is equal to y, right? Okay, so to make this easier, what we can do is we can define 2 additional variables, let's say f, which is equal to either 1 or 0 if the first is gold or if the first is silver. Okay, so f is a random variable that returns 1 if the first drawn is a gold, second one, the second one is going to be multiplied by like, well, here it uses s, don't want you to be confused, let's say h, okay? And h does the second one, so it's 1 if the second draw is a gold, and 0 if the second draw is a silver, okay? Now with these 2 random variables f and h, we can define x and y in terms of, right? Because we're just drawing twice, so we have a random variable for the first draw and a random variable for the first one. So clearly we can see that x is equal to f plus h, right? Mm-hmm. Because in fact x is the number of gold coins drawn.
Right.
And then y is in fact going to be 2 minus x. Right? Because y counts the number of silver coins. So if we draw 2 gold coins, then I get 0.
Right.
Right? And if I draw 2 silver coins, then I get 2, and so that's why I say it's 2 minus x. So actually I can think of this also as 2 minus f minus h. Now, what we can observe is that these two events are independent. Yes? And the probability of f being equal to 1 is in fact the same as the probability of h being equal to 1. And they are both equal to 4 over 7, because I have 4 gold coins over the total. So now what's the probability? What's the function fxy calculated in y1, for example? This is the probability that I get exactly 1 gold coin and 1 silver coin. Yes? So that is the same as the probability that that f is equal to 1 and h is equal to 0, plus the probability of f equal to 0 and h equal to 1. Right? So I either pick the gold coin at the first, and then the second one is silver, or vice versa. Now these events are independent, so that is the same as probability of f equal 1 times probability of h equals 0 plus probability of f equals 0 times probability of h equal 1. See, I'm decomposing it.
Could you log h?
Of course I could.
Yes.
I should keep going to do that. So now this is going to be 4 over 7 times 3 over 7 plus 3 over 7 times 4 over 7, which gets me my result, which is 24 over 49. You see, it's about half. It's about half. I don't need to calculate it, right? It's nearly 25 over 50. It's basically 0.489. Cool. So the probability of drawing 1 gold coin and 1 silver coin is actually about half. Okay, so we can similarly compute other things. Now, of course, these were easy because x, y were independent. But if we do this without replacement, and the things change, and the events are not independent anymore, and then you have to use conditional probabilities, right? So when you get to this point, I cannot simply put the product here because the events are independent. If they are not independent anymore, clearly this becomes instead the probability of h equals 0 given that f is equal 1. So if I draw the first gold coin, then what's the probability of the second? And then I multiply this times the probability of drawing the gold coin at the first. And then what's the chance of drawing it the other way around is the opposite one, right? So it's probability of h being equal to 1 given that f is equal to 0 times the probability of f being equal to 0, right? And I do this because obviously f is the first one that I do, right? So that's why I do first f, and then I multiply what's the probability of h being something given that f is that, right? And if I compute that, then I get a slightly different value. In fact, I get about 0.57. So actually a higher chance of having a 1-1 split, right? If I don't replace the coin, which is interesting. So it's important. It's an important example. Of course, we can use random variables to model other things, and to conclude, what we can do is remember that we had Bayes' formula. And so we can translate this to the case of random variables as well. And if we have two random variables, x and y, then we can write the f x given y of x, y is given by f x of x times f y given x, y x. This is y given x. This also should be given. Okay. Divided by f y of y. So we have to assume that f y of y is bigger than 0, of course. Okay. And this is the same as the Bayes formula that you saw for just normal events. Now you can actually translate it to random variables. Okay. So you have another example on the book that uses Bayes' formula to calculate stuff. This is basically just tools still that we're kind of putting other around. Okay, so the last tool that we need to put, it's maybe arguably like one of the most important, and is the idea of expected value. Okay. Okay, so what is the expected value of it? Now that we have random variables, right, we can actually use them to do stuff. Because the thing with an event, right, is that now random variables count stuff that happens. So if I have a random variable x, in one sense, the expected value is exactly what the word says. It's like what we expect to happen. Right? So you can read this as like, what's the expectation? In practice, this means the average of what? The average of the result weighted with the probability of each thing happening. Right? So it's a very accurate measure because it tells you if you average the results, like yes, I could get this, but it's very unlikely, and then I can get this other, but it's like a lot more likely. And when I average it, and each event, each occurrence of the random variable value happens with a certain probability, then I put it all together and I get like what's the expected thing. Right? Which again, going back to our original idea, like gambling and games and stuff, this is kind of what you want to have in mind, because of course you kind of know what's the odd. Right? Sometimes you don't want to know. Okay, so it kind of gives you an indication of the behavior of x. So let's define this clearly. This is defined as a quantity E of x, right? Which is the sum. Of course, as I said, we're doing an average, right? So it's the sum of xi, which is the value that the random variable can take, times fx of xi. Okay? Why fx? Because this is the same as the probability of x being equal to exactly that. Okay? All these sums go from like 1 to n. Assuming that my random variable can take like n different values. Okay? So I'm assuming that x can take the values x1, xn, which is the case in a lot of situations. Okay, so it's really, you see, it's like a weighted average. Sometimes also mean. Yes. So what is the most blatant case of like expected value that we have in mind, right? Let's consider x to be the random variable of the sum of two dice. Again, I'm assuming like 6-sided dice. Okay. So this sum can take the values 2, 3, all the way up to 12, right? Okay. So what's the expected value if you roll 2 dice? You know? You got it? No or don't know?
No.
Okay, well, somewhere in the middle, right?
Yeah. Somewhere like
Around 7 or something like that.
7 is the answer.
Okay, yeah.
And you can actually calculate it precisely, right? Because when you do this, the expected value of this random variable is the sum from 2 to 12, right? To be mathematically precise, it will be from I equal to 2 to 12 of xi, probability of x equal xi. Yes? So it's basically 2 times the probability that x takes 2. What's this probability? Both guys have to show.
1 out of 36.
Yeah, so it's 136, right? And then 3, how many ways can you get 3? 2 ways.
2 out of 36.
Right? So 2 out of 36. And then 4, you see? Now 4 you can have 1, 3, 3, 1, and 2, 2. Right? So you have 3 out of 36. And you can do your mathematical thing, and then you can see that actually it peaks, right? It peaks here in the middle, 7. There is exactly 6 over 36 ways. Right? You can have 1 and 6, 2 and 5, 3 and 4, and then the other way around. Okay? And then it decreases all the way back. Of course, you can only have 12 if you have 6 and a 6. So that's 1 over 36 again. So it's kind of like curved thing. And when you sum all this, you actually get exactly 7. So 7 is the exact expected value in the roll of 2 dice. It makes sense because it actually is the most likely event to occur in the first place. And when you sum all the probabilities with the average, with the probability, then you get the expected value is 7. So basically, when you roll 2 dice, you can expect that a 7 is something that is on average achievable. Lower than a 7, you're probably going to have a good life. If you need like a 9 or a 10, tough odds. Okay? But in fact, this then depends on what you're doing with the dice. So this is just like to introduce you to the idea of expected value. Okay. So now, of course, the name expected value is good in a sense because it tells you like what the behavior is supposed to be. But in a sense, it can also be misleading because you're like, okay, this is the expected value, and sometimes this is actually not a value. For example, what happens if I take x to be just one die? Right? What is the expected value of like if I roll just one die?
3.5.
Exactly. It's exactly that, right? Because you would get e of x, and this is 1 with probability 1/6, and then 2 with probability 1/6, right? They all have equal probability, and so this sum is actually 7/2. This is actually not a value on the dice, right? And so this is why you have to understand that the expected value kind of tells you what the behavior, like it's going to tend towards that, but it's somewhere in the middle. In this case, because it's a mean, and it's in the middle because this is our fair and balanced dice. Yes, but it may actually not be an actual value that you can obtain. Okay, so if you just roll one dice, because it's 3.5, for example, it's fair to say that it's around 3, right? So one time you get 3, one time you get 4, or something like this. Yes, but of course, again, we are only taking the situation where the dice are balanced. Now, of course, the idea of expected value becomes much more interesting if, for example, the dice is fake or like cheating, and then like like one side is more likely than the other one, and then like all the probabilities mean instead of having 1/6 and 1/6, then the 6 happen with probability like 2/8 or something, and then like all the probabilities are like remixed. Like remember, the sum still has to be 1, right? But you can like push them towards an extreme if you have cheating dice, right? So that the 5 and the 6 are more likely or something, right? And then like the expected value shifts, instead of being 7, maybe becomes like 8.5 or something, right? And then like that gives you a big advantage, and so on. Okay, so what happens is the expected value of a random variable that is uniformly distributed. So if I have a uniform distribution of from 1 to n, then I expect to have n plus 1/2. Okay. Now let's in fact go to a coin tossing experiment where we can modulate things a little bit more. What's the expected value here? Right. So let's take the heads is probability p and the tails is 1 minus p. Okay. Classic situation at this point. We've seen it already more than once. And then let's have again x, which is the number of coin tosses before the first head. Right, so basically we say that x is equal to n if the heads appears as the nth toss. And then of course we've seen just before that this follows the geometric density. And the density function is given by 1 minus p to the n minus 1 times p. Yes. So it's like 1 minus p, the n minus 1 times p. Yes. So then the expected value would be a sum, right? And it's going to be n p 1 minus p to the n minus 1. And I'm going to iterate over n. Here is just using I use n is the same thing. It's just an index. And what is curious is that actually I can count until infinity. Yes. In principle, I could have like like I'm really, really, really unlucky. It's not unlucky anymore. It's uncanny, but like like I can just keep tossing and keep getting tails. Okay, so it's important when you model that. And now, perhaps this is a little bit more interesting to see explicitly. This is an infinite series, so this is equal to minus p sum of if you so basically what you can do to calculate this is you can take the derivative, right? And so you can take the derivative with respect to p, and it becomes 1 minus p n. So you differentiate that, and then this is always the sum from 1 to infinity, and then this is minus p. The derivative of sum is the sum of the derivative, so I'm taking its derivative out. Sum 1 minus p to the n. P goes from 1 to infinity. N goes from 1 to infinity. Okay, and then this is equal to minus p times the derivative of what is this sum here? Now you can recognize it is exactly a geometric progression, right? So yeah, it sums as 1 minus p minus 1. And then when you take the derivative of this, you will get e over p squared. And you multiply by everything. So the derivative of this will be like minus 1 over p squared. This part minus 1 over p squared times 1 minus p is plus p over p squared. Okay. And this is just 1 over p. So then we get the expected value is actually 1 over p. And it depends, which makes sense, depends on what your probability is. So how many tosses do you have to get before you get a head on average? Well, it's 1 over p, right? So if your coin is balanced and p is 1/2, then it's 1 over 1/2, which is 2, which again makes sense, right? If you have exactly 1/2 chance of getting your head, then you should try twice. If your chance is p lower, then you try like 1 over p times. Okay, so for example, if p is 1/3, then you have to try 3 times and then work out. Okay, so this concludes kind of like our initial tool belt. We now know what the random variables are and what expected values for random variables are. Now we can start looking at algorithms for cryptography, which are, of course, of interest to us. And in particular, one thing that we can now model a little bit more interesting is collision algorithms. We have already seen and hinted at the fact that looking for collisions is always a more efficient strategy than just going through a list, right? So the core idea is that if we, instead of looking through a list, we just make smaller lists and look for a match instead, and that's much more efficient. Okay, and before doing this, because I think I did mention this, and the response was no, like, oh yes, I know this. So we have to take a step back and talk about the birthday paradox, which I'm sure you'll find interesting. Okay, so what's the birthday paradox? The name comes from the fact that it corresponds to the idea of like looking for birthdays in a bunch of people. Yes? And so consider the two questions. What's the probability, right, that someone has your birthday? Okay. And question 2 was the probability that at least the people share a birthday. Okay? So they look similar, but they're not the same question. Okay? So let's answer the first one first, because it's the easiest one. Basically, if you have a birthday, it's going to be one day of the year, and roughly a person has like 1 over 365 chance of having your same birthday, right? This makes sense. So, for example, if you take 40 people, say like classroom size, then you get 40 over 365, which is about 11% chance. Okay, very simple. Of course, this is an overestimate because it double counts some stuff, like more than one person could also share your birthday, although it's unlikely, but so you're not counting exactly correct. So what you could do instead, to be precise, is to count 1 minus the probability that no one shares your birthday, right? So if you count as 1 minus the probability of none of the 40 people has the same birthday as you, then this is 1 minus the product of the probability that, say, the ith person doesn't have your birthday, right? From 140. Of course, every person has the exact same chance of having your birthday or not having your birthday. So if the chance of having your birthday is 1 over 365, then the chance of not having your birthday is 1 minus that. So it's 1 minus 364 over 365 to the power of 40. Yes? And now if you do that, you get approximately like 10.4. So it's a little bit less than the 11% because the 11% was actually, overcounting. Okay. Okay, so if you take 40 strangers at random, then you have about 10% chance of someone having the same birthday as you, which kind of makes sense. Now, okay, consider the second question in which you say, okay, take 40 strangers at random. What's the probability of at least 2 of them actually sharing a birthday? It doesn't have to be your birthday though. Okay. What's the probability of them sharing at least a birthday? We'll use a similar type of computation, right? So basically what we can do, what we can do is compute the probability that people have the same birthday as 1 minus the probability of all 40 have different birthdays, right? You see why it's important to use the complement, right? We're already using it twice here. So this is going to be 1 minus the product from I equal to 1 to 40, right? What we have to count is that at the beginning we have 1 guy, right? Then the second guy has to be different from the first one. And the third has to be different from the previous 2, right? So is that the ith person is different from the previous I minus 1. Okay? And so this we can count. It's not hard, but it's 1 minus the product, 1 to 40. It has to be 365 minus I minus 1 over 365. Okay, so it's even easier if you write it out, because the first guy can have any birthday, and then the second guy can have any birthday but the one from the first guy, and then the third guy can have any birthday except the previous 2, all the way down to 326 over 365. Okay, so if you write it out, it's not, this is more precise, as is usual with summations, and this is more intuitive. Okay, in the end, it doesn't matter, but what turns out is when you compute this number, you get about 89%. Okay, so if you take 40 strangers, there is almost a 90% chance that 2 of them share a birthday, which is a lot less intuitive than the previous result, but it's just the way the probability works, because you're not committed to a single date. Mm-hmm. And this always blows me. I mean, you guys are already more mature than like my, say, calculus students, right? And like when I say this to like first year college students, like blows their mind, because it's like, wow. Like, so basically, if you take 40 people at random, you're almost certain that you have a birthday in common. And no one ever thinks about that. But in fact, okay, we can, basically what the important part is this formula here, where we're considering that the birthday is different from the I minus 1 previous ones. Okay. So the answer to the two questions is fundamentally different, and the fact that they do not is why this is called a paradox. Okay? And in fact, one thing that is more useful than this, even, is that you don't want, like you have 89%, which is huge, right? But a lot of the times you're not necessarily restricted to having 90%. You don't want the absolute thing. You may be happy with having like a 50% chance. And so you can ask, okay, what's the minimum number that is required for me to say have like a 1/2 probability? Okay, I take X many people, and with 1/2 probability, I have this collision. Because ultimately, this is what I'm looking for. You see where I'm going? Like this is the birthday paradox.
Right.
But now we're going to use it in stuff. And trust me, you use it in everywhere, not just in cryptography. And the thing is, it in fact requires only 23 people if you're talking about birthdays. So even a much lower number to have about 50% chance of having a match. Okay. So what we can do now is generalize this. Of course, we don't care about birthdays, but we do care about using the same principle when counting stuff. Okay, so now here's where we get to collision algorithms. Okay, so this was like a step back, but the idea is that essentially it's a lot more likely. There's this paradox for which like finding a match is actually very likely, even with like restricted sample space, essentially. And so, yeah, so basically, if you take n numbers, and this is a very rough approximation, but if you already have like about square root of n, then you're very likely to find a match. And if you take the square root of 365, you'll see why you get the number that you get. Okay, but we can actually count more precisely. So say that an urn contains n balls, and I have, say, n, what is it, like red, and then n minus n blue balls. Blue, okay, red and blue. So what you do is the same experiment that you did. You draw one, put it back, draw it again. Okay. So you pull out n balls. Okay, one at a time, and with replacement. Yes. Okay, so the probability of selecting at least, so first of all, what is the at least one red ball? And then what's the probability? So let's do the first one first. Then the probability of at least one red is actually equal to 1 minus n over n to the power of m. This is the number of red balls. This is the number of draws that you do. And that's the total. Okay. In fact, you have a lower bound, which again, in a lot of cases, is what we're happy with if we're looking at algorithms. Right? The probability of at least one red is, here we have an equality, right? But lower bound would be that the probability of at least one red, let's be precise, is at least 1 minus e to the minus mn over n. Okay? Wow, where does this exponential come from? Okay? So yeah, so basically the idea is this: each time you select a ball, you have n or big N chance of getting a red ball. So you would think that you do this m times, and then the calculation is pretty easy. But of course, if m is very large, then this will take you to a probability that is like bigger than 1, right? So it cannot be. So you have to count again. The difficulty is the same as we had before, that you were overcounting, right? There's a possibility that, okay. So if you don't want to overcount, what you have to do is exactly the same thing that we already done twice. Count as 1 minus, right, the probability that you have m blue balls. Right? That's a lot easier and also a lot more accurate. Yes, and so you can compute this as 1 minus the product of the sampling a blue ball, right?
Yeah, can you slide it up?
Yes. So it's the product from 1 to m of ith ball is blue. And of course this is 1 minus the product of n minus n over n. That's the blue balls. From 1 to m. And that gets you the formula in the end, which is this one. For the second one, the trick that you use is that you use the fact that e to the negative x is always at least 1 minus x. This is a well-known thing from calculus. Okay, and so what you can do is you can use this fact. If you set x equal to n over n, which is exactly the red balls. Yes, is exactly the proportion of red balls. So if you do this, you take this, right, and you take the power of m, and you use the inequality, then you'll get your result. Okay. So in fact, this result is what people care about, and is almost equal when two things happen. Basically, n has to be large, and m and n are both above the square root of n. Okay. And then you get almost an equality in that case. Cool. And you can see already that this is kind of like a case of interest for us. So what we do is basically when we look for collisions, we see our list, right, of capital N. And then basically we make our first list of a bunch of balls. And it's kind of like what the book says, like kind of like you have blue balls, you take some of them and then you like repaint them red, put them in there, and then see if you can find a match, essentially. Okay? Because at that point, finding a red ball is the same as finding a match between the lists, because the red balls like where used to be the blue balls before. Okay, so it's so you have more examples in the book, and with deck of cards and stuff. But what you want to take away from this is that essentially matching is much easier than going through the list to find things. And so we have these collision algorithms. They also go by other names. Sometimes you just say it's a Berde paradox algorithm. Anyway, it's like a collision algorithm. It's based on the Berde paradox. Sometimes you refer to this as meet in the middle. Yes. And sometimes they're even called like square root attacks, because basically it takes like a square root number of attempts. Okay, and you can do this in cryptography everywhere. Like it's a very generic tool. For example, the stuff that I do that deals with like codes and bit strings and stuff, right? Basically, what people do is like you have a certain bit string of a certain weight, so like a fixed number of ones, right? And instead of, say you have like a bit string that is like long 100 and has like 8 ones, right? Then basically it's faster, rather than going through all the possible strings with 8 ones and length 100, right? Is to split and look for like 4 ones in these positions and 4 ones in these other positions, and then like trying to match them, right? And then see if that works. And that slashes your running time by a lot, or by the square root. Okay, so people are very creative with this. Basically, every time you can like make lists and try to find a match in a creative way, even though it's even counterintuitive, because you're like, okay, what if so like basically you set up a bunch of possibilities. It's like, okay, let's try to find 4 ones here and 4 ones there, and see if it works. If it doesn't work, let's try to find 4 ones here and 4 ones. Okay, and then you set up this parameter, and this is much faster than just going through all the possible combinations of strings of 8 ones. Yeah. So it's very clever, and we can certainly use it for solving the algorithms that we have seen, namely the discrete logarithm problem. Okay. So what happens to discrete logarithm with collision algorithms? Okay. So For sure, we have at least one that we already saw, is the baby step giant step. Okay, and it solves the DLP in approximately square root of p steps if this is my discrete logarithm over fp star. Yes. Of course, we also have seen the index calculus for DLP, and this is faster, right, than the baby step giant step, if this is the classical discrete problem. But what we said is that, for example, in other groups, like elliptic curve groups, then you don't have index calculus equivalence. And so collision algorithms are important because they do represent the best attack. Okay? So let's try to look for like a black box generic DLP. Yes, in which you have a group G, and then let's take an element H of order n, so that H to the n is equal to the identity. Okay. And then we are given a different logarithm problem, h to the x equal b. I'm using like extremely generic notation so that we can study this collision algorithm absolutely in general. Okay, and then what we claim is that we can find a solution in square root of n steps. Well, n is my order, right? And each step is a group exponentiation. Group exponentiations. Okay. So the basic idea is this. X is my discrete logarithm. I will write it as y minus z. You see, I'm already setting up a split. Yes. And then I will write that h to the y is obviously equal to b h to the z. Okay? Because h to the x is h to the 1 minus z. So I get h to the y times h to the minus z, so I just divide, which means I take it on the other side. Okay, so then this is the base to build my new lists. Yes. So then what we do is we do one list of h to the y values. This is one list. And then we'll do the other list having the b h to the z values. You see, I'm kind of like taking some blue balls and then I'm painting them right. And now I'm going to look for a match between the two lists. So I do h to the y for a bunch of random y's. I then do h to the z times b for random z's. And again, the clever way to do this, remember we already saw it for baby step giant step. We take bh and then bh squared, like we just keep. So we can do this even efficiently. And then when you find a match, you actually find this, which means that you have this. Yeah. Okay. So let's count why this is exactly square root of n. Basically, you choose random exponents y1, y2, yn. Yes. And then you compute all these values in the first list. And so basically, we are selecting approximately n elements out of the set S, which contains 1, h squared, all the way up to h to the n minus 1. Yes? Which is my, because my element has order n. Now, I didn't say that this was a primitive root, right? So it could be not the entire group. But anyway, it's the group generated by h, blah, blah, blah. So I'm kind of selecting little n elements out of this, which is n elements. So I'm kind of selecting little n out of big N by this first exponentiation process. And then you do the same with the second one. And we also get a subset of S. Maybe not exactly the same ones. In fact, like I hope to just find one match. I don't think that there's going to be more than one overlap, right? So really, you can see the first is saying you select little n elements from the urn, and then you want the probability of selecting at least one red ball. Is what we had before. So is at least one match between these and these, and you can count it like we counted before. and you get that this probability is 1 minus n over n to the power of n. It's the series, this is the result that we had before. And this is approximately 1 minus e to the power of minus n squared over n. So it's n squared now instead of being m times n, because the number of balls that we extract is the same as the number of lists. Okay? Before we had like, oh, I have like n red balls and I draw m of them. Now these two numbers are the same, so I get n squared, yeah? Before this was m. So yeah, basically I get this. And so what you can do is if you choose, say, n to be approximately 3 square root of n, for example, which is order of square root of n, and then compute, then this probability boils down to about 99 or 98% of getting a match. So basically, you're guaranteed to find a match. You just have to choose the size of the list about 3 square root of n. Okay, and so if that is not good enough, then you can take n even bigger. You can take n, say, about 5 square root of n, and then your probability of success is 1 minus 1 over 10 to the 5. Okay. Actually, no, that's not true. It's 10 to the 10. Okay, so 10 billion. So it's a pretty good chance. Okay, so as soon as you find a match, then you solve the DLP, and then basically you're done. So how long does it take to find this? You basically 2n steps. It's 2n steps to build the lists. So it's twice whatever value you took for n, square root of n. So it's still order of n. Sorry, order square root of n. And then we said that it takes approximately like 2 log whatever j, where j is your number of bits. So sorry, the log j is the number of bits. J is your integer that you're considering. Okay, so it takes about, let's say, in general, about 4n log n multiplication to put together two lists. And then you just check. And the check is easy, and you can in fact you just do in total like something like n log n comparisons. And if you take, for example, this value here, when you put it all together, the computation time is in the end about, say, 13.5 square root of n log, or 1.3 times n. Okay, which is essentially square root of n dominating, because this is logarithmic. Okay. So we can do this. There's a numerical example in the book. And we'll just do one example, and then next time we'll see how we can do this better. Because of course, one problem with this is that we have to store the list, or at least one list.
So that's square root of n space as well.
It's going to be exactly. So it's going to be this much space, because we can at least say store one list and then do the second one live. Like instead of storing the two lists and checking, you do one comparison at a time. And so you just like do one list, but it's still square root of n. And if n is big, then of course that's very big. So we can see a better algorithm next time. So let's finish with the example here. Do you have any questions? More questions?
In practice, though, the space isn't probably the main constraint.
Well, it depends. It's not something that can be ignored. There are algorithms that become more and more efficient. What I was referencing before as well, when you look for like binary string of a certain weight, the same thing. You can say naive way, brute force. You're looking for a string long 100 and has like, say, a fixed number of ones. Okay, you can just try all the strings with that number of ones. And then like there's no space necessary. You just do a search. Of course, that's stupid. Then you can do better things. The more you add, the more the space requirements become. And at some point, you're never sure anymore whether the game is worth the candle, like we say in Italian. Like basically, if it starts being a little bit too heavy, then sure, maybe maybe you do gain, but you gain like a couple of bits time complexity, but then your space requirements are doubled. Is it really worth it, right? So because you can do more sophisticated things. The easiest thing you can do is a simple birthday paradox thing, where you look for you split your number of ones halfway here and half there, and then you see if that's a good match, and if it doesn't match, then you do the split again. Then you can do, okay, instead, why does it have to be half? Maybe I put 2 ones here, and then I look for the other ones, or 3 ones here. And then you can see, oh, let's fix some positions in which for sure I don't have ones. Let's put a 0 window here, so like you can make the algorithm more and more and more refined. But then the complexity grows in terms of the space complexity, you cannot exactly ignore. And if you were just trying to do the basic baby step giant step with the huge space complexity, it is actually impractical. Because you have 2 to the 1024, and it's a big number, even if you take the square root. So yeah, you cannot ignore space complexity, even though people tend to focus only on the time complexity, of course, most of the times, but not all the time. And then, of course, this is when we talk about, for example, classical systems still, right? Now you can understand that if my algorithm is very efficient, say, for example, I'm looking for a quantum algorithm on a quantum computer, then of course that's really expensive, because quantum bits are really difficult to obtain and to maintain and to operate with. So then the space complexity makes a really big difference. Like, so the kind of circuit that you use really does have an impact. But even on classical situations, that's already something that you cannot necessarily ignore. You just say, check that it's not a problem. If it's not a problem, focus on the complexity. But if it does grow huge, then it is a problem. Okay. So yeah, so let's finish this, since we have a few more minutes. Suppose that we're trying to solve this discrete logarithm problem. 2 to the x equal to 390 in f 659. So p is 659. Okay, this number actually has maximum order, meaning it's a primitive root. So order of 2 is 658. Yes, it's p. Great. And so now what we do is just we choose a bunch of random exponents for h. H is equal to 2, right? That's my h. And so we just basically do h to the t for a bunch of random exponents, and then b times h to the t, another bunch of random t's, and then we look for a match. So you have these results here. I'm not going to write all of them, right? You find first random number t, you get h to the t, h to the t. Then you do another one, then you do another one, then you do another one. Finally, you find that this 422 is equal to this 422 in the first list. And so the exponent 564 for the second list is same as 83 for the first list. Okay? And look how many steps you did, not very many. Okay, so you obtain the 2 to the 83 is equal to 390 times 2 to the, 564. Okay? That's from the first list, and then from the second list. Once you do this, this is 422 in both cases, right? And so the two lists actually only had length 18. Very short. And we have solved a discrete obviously we solved a discrete problem because then we have the 2 to the 83 times 2 to the minus 564 is equal to 390, right? And this is the same as 2 to the 83 minus 564. Compute that, that is 2 to the 177 in your field, and that's your discrete logarithm. Okay? So basically, this was a short numeric example. It's actually a lucky example too, because with lists of length 18, the actual chance was about 39% of getting a match. On average, you would have expected maybe like a list of length 20, or I don't know, right? But already it just goes to show that it happens. with a very reduced number. Of course, this is you can compare this to the square root of p.
Wait, 177.
177. That's your yeah. You take modulo, right? You take modulo p. Yes, that's 2 to the negative 481. So it's 177. Okay. So if you take the square root of p, which is, let's say, what was it, 659? Square root, about 25. Okay, so that's why it was a little bit less than. So at least 18 was a little bit shorter than what we expected. Okay, but of course you can see that it's a very efficient algorithm, at least time-wise. Cool. So yes, then we can next time look at more complicated, sophisticated collision algorithms, and then that will lead us into the conclude, if you want, the first part and lead us into the second part. Okay, but this was an important. So we're not gonna. I think this is the entire baggage of probability theory. It was a lot, but it's all in section 4. So section 4 is all there, and of course, one could and should do an entire probability course because it's always something that comes out handy. A lot of things, whatever type of mathematics you do, a lot of things come down to probability as well. Like if you do analysis and big differential equations and stuff, in the end, like always you want to know, for example, what's my probability of my method to succeed, and so whatever you do, the probability is always a very good tool to have. In this case, for us, it means in cryptography the ability to analyze algorithms first of all, in terms of like chance of success and stuff. But you can do, remember, if you're good in probability and statistics and distribution, you can do a lot more. You can actually do better attacks. Yes. So it is really an important skill. Okay. So that is all I have for today. I don't want to overload it. I'll see you guys